it's going to be a very interesting class as we take ourselves through univariate probability distributions, which is very important in data science because we use probability distributions to model the behavior, the random behavior of data sets. And in this case, we're going to be considering just univariate probability distributions because there exist multivariate probability distributions. The difference being that for the case of univariate, we are dealing with just one random variable and the set of observations that this random variable generates. For the multivariate probability distributions, we are dealing with several random variables and also their corresponding observations. So, for example, we can have a bivariate probability distribution. If it is bivariate, it means we have just two random variables. Okay, we have two random variables. If it is trivariate, we have three random variables. And of course, anything greater than three, we generally call it multivariate. Okay, so but our discussion this morning is just going to be based on univariate probability distribution. Okay, so let's see what we have for today. This is just what we're going to be discussing, two major points here. We're going to look at, we just introduced probability distributions, and we also talk about the properties of probability distributions. Okay. All right. You know, in probability theory and statistics in general, we've often talked about random variables. I think in the previous classes we've talked about random variables. And we actually saw that random variables are functions, okay, that assign a numeric value to each possible outcome of a random experiment. For example, if we toss a coin, we are going to have either head or tail. And what is of interest to us most times is a specific value or a value that we can assign to this outcome, because having a head or a tail does not really prepare us for further analysis on the outcome of that random variable. Okay, so what we do is, if we do have a head, we can assign a value of 1, given the fact that the outcome of interest is having a head. So we can give a value of 1, and if we don't have a head, in which case we have a tail, we can assign a value of 0. So that is what a random variable is. So a random variable is actually a function that that is defined on a sample space and brings out what is called a real number, as we can see here. So this is the mathematical representation of a random variable. So if X is a random variable, it is defined on a sample space. And of course, it emits some values which are real numbers. Okay, so it is these real numbers that we are interested in. So it's a function that assigns a numeric value to each possible outcome of a random experiment. Now, this sample space here is a set that collects all possible outcomes in an experiment. This is a set that contains all the possible outcomes when we perform a random experiment. So what we do is, just like we have functions, okay? When you have a function, say f of x, you agree with me that there is what is called the domain of the function, okay? There's what is called the domain of a function. The domain of the function is the set of values that the function takes in order to generate an output, okay? The set of values that the function takes in order to generate an output. Now, for random variables, the domain of the random variable is this omega, which is the what? The sample space. Okay. Now, this sample space contains all possible outcomes that the random experiment generates. For example, if I flip a coin, a single coin, the possible outcome, the sample space is just going to contain two outcomes, which is a head or a tail. So if I say head is a random, X is a random variable. If I say X is a random variable, it means this X is a function that is defined on this sample space. In other words, all possible outcomes for X, okay, if X is a random variable, it means X is defined on this sample space, omega. Okay, it's defined on this sample space, omega. In other words, the domain, the input that X takes are all the outcomes that are in omega. However, the function proceeds in such a manner that it processes these outcomes. It processes points on this set, omega, to produce a real number. That's what a random variable is. X is a random variable that talks about the possibility of obtaining a head when we toss a coin. So what happened is, in the entire sample space for that experiment, we know the outcomes are either a head or a tail. So what happened is that the function, the random variable as a function, assigns a value for all these outcomes. If it is a tail, the value is going to assign to the outcome tail will be what? 0. If it is a head, the value that the function we assign to the outcome head will be what? 1. So you discover that 0 and 1, which are the outcomes which the function processes, are actually real numbers. Meanwhile, the sample space itself is not a real number. I mean, it's not a set of real numbers. It's just a set of what? Possible outcomes. It's like throwing in something inside a machine and asking the machine to generate numbers. Yeah, that's a very good way of explaining it. It's like I have a machine. We all know that we can use the methodology of a machine to explain what a function is, right? So if I throw in some outcomes, whatever the outcome is, it could be that I got a 6, I got a 5 when I, roll a die. So those a 5, a 6, a 3, a 2, they are really not numbers, they are outcomes. However, we tell the function to assign specific numbers to each of these outcomes. So the function, the random variable, is that function that processes these outcomes to generate the numbers. And at the end of the day, what it generates are actually what? Real numbers. And when these real numbers are generated, they become very useful for further statistical analysis. So that is just the idea of a random variable. Okay, that's one way we can explain the idea of a random variable. Okay, so let's proceed. So in previous discussion, we've already said that random variables are either discrete or continuous. Okay, random variables are either discrete or continuous. So discrete random variables, they essentially take countable numbers of values. We can say they take integer. We can call them integer value random variables. They are discrete random variables. They take countable numbers. We all know what countable numbers are. When we say a number is countable, it means they are specific. They do not contain decimal points, okay? Or whole numbers. We can say they are whole numbers, okay? So discrete random variable takes a countable number of values. For example, if X is a discrete random variable, it means X will take this set of values. You can see the set of values. It takes 0, 1, 2, 3, 4, like that, because we know that we can count with these numbers. We can count with 1, we can count with 2. I mean, these observations that these random variables takes, they are countable numbers. They are numbers that we can count. There are numbers that are uncountable. So continuous random variable takes uncountable values in an interval. Okay, they take uncountable values in an interval. For example, if x is continuous, we can say x takes value in this interval a and b. Okay, a comma b. Now, this is an example of a closed interval. It means x can assume a value of a, it can also assume b. Now, if we say a is 5 and b is 7, okay, a is 7, it means the values that this random variables takes begins from 5, then 5.1, 5.2. Now, there are several observations. They are actually uncountable values between the interval 5 and 7. There are many observations that they are uncountable. Okay? They are uncountable values in that interval 5 and 7. So this is an example of a continuous random variable. It takes all observations in an interval. Whereas for the case of a discrete random variable, they take specific values. Okay. Of course, this is the case of an open interval where the random variables assume values between a and b with a and b not included. This is a half-closed interval where the random variable takes values between a and b, a included, b is not. And of course, here is also another half-open interval where the random variable takes value between a and b with a not included, but b is essentially included. So this is what we have. So when we talk about random variables, we have discrete and continuous random variables. So we've I'm just trying to refresh my mind on this. Yes.
Yes, sir. So I'm looking at this random variables, either discrete or continuous. The random variable here is the function itself, right?
Yeah.
So whatever is going inside can be discrete or continuous, but the outcome must be discrete, as in must be an whole number.
No, it mustn't be an whole number. I understand the example I gave with the flipping of a coin, right? That's an example of a discrete random variable. Okay?
Okay.
That's an example of a discrete random variable. Okay? If it's a continuous random variable, the value it takes needn't be just countable observations. Okay?
Yeah.
I don't know if that helps. Okay. Okay, for example, if I perform an experiment, I can design the experiment in such a manner that the outcome of that experiment, if I use the random variable to transform the outcome, it gives me observations that are not, essentially discrete. If I come to the class and I ask everyone their age, okay, ask everyone their age. You see, there's going to be an outcome. What is the outcome? The outcome is that everybody in the classroom has, I measure your weight. Okay, let me use the weight. If I measure your weight, everybody in the classroom, you see, the outcome exists that you're going to have a weight. I mean, there is going to be the amount of kilograms you're weighing. Okay, now that is an outcome, right? So what the random variable does is that it transforms a particular outcome, which is, I mean, the reality that is consistent with one individual with respect to weight, to a value, okay, to a particular value. Okay, so what's the value? If I ask you, maybe we take the measurement of your weight. Of course, the idea that your weight exists is the outcome. So, but it is going to generate a value. What is the value of that experiment? Maybe you weigh 6.5. So in this case, see that that's an example of 64.5 kg, right? So in this instance, you see that it is not it's not essentially a discrete, outcome that is resulting. Okay, so that's what how random variable exist. Okay, they are discrete and they are also continuous. All right. So probability distributions. What then is probability distributions? Okay. So a probability distribution describe how values of a random variable are distributed. Okay, how values of a random variable are distributed. If you see, like in the coin flipping experiment I described, okay, what are the values of the random variable if I flip a coin? If I flip a single coin, the value of the random variable is just going to be 2, 0, and 1. 0 if it returns a tail, and 1 if it returns a head. Now, probability distribution helps us to describe how values of random variables are distributed. Okay, further, it tells us which value are possible and how likely they are. Put differently, probability distribution helps us to compute the probability of the values assumed by a random variable. That is what probability distribution helps us to do. So it serves, probability distribution serves as statistical models. Okay, they serve as statistical models that helps us to, compute how likely, the likelihood of the values taken by this random variable. Yes, that is what probability distribution helps us to do. So I'm going to give you guys an instance. I mean, as data scientists, you play with a lot of data. I mean, you're giving data sets on anything and you're asked to, just work on this data. Say you have 50 observations. Maybe you generated this data from an experiment. It could be that you ask people in a class their age, and then they tell you their age. Now, the age they tell you is actually the value assumed by the random variable. What's the random variable there? Age. Now, sometimes you might be interested in the probability that a specific individual in that class would be 24 years old. Okay, will be 24 years old. That might be something of interest to you. That, yeah, what is the probability that an individual in this class is 24? Now, first of all, what probability distribution does is it helps you to keep track of the distribution of age in that class, the distribution of the data. Like, for example, you want to know the minimum value, the maximum value. You want to know, I mean, you just see the spread of the data. You want to see the spread of the data. You want to see, the kind of the various angles of that data. So then further, you begin to compute the probability of specific outcomes of, I mean, the specific values of that random variable. So that's a probability distribution. It is used to describe how values of random variables are distributed. Okay. It tells us which values are possible and how likely they are to occur. Now, for example, in a class like ours, it's almost, if I want to ask you, if I ask everyone their age in this class, we cannot have someone returning an age and say, oh, I am minus 20-year-old. In other words, the value minus 20 is not a possible value in the distribution. Okay, because age cannot be negative. It's not a possible value in that distribution because age cannot be what? Negative. So probability distribution tells us these values. And as we proceed with the lecture, I'm going to give you more hints about this. So it tells us which values are possible and how likely they are to occur. Okay, now when we talk about how likely they are to occur, it gives you an idea about what? Computing the probability of their what? Occurrence. In a class like ours, I can say what's the probability that an individual would be 30 years old. Okay, what's the probability that an individual will be 40? What's the probability that an individual will be 12? Okay, I mean, we can do that. So we use probability distribution to do all of this. So the process of doing this is we using probability distributions to model the data. And it's a very important aspect of data science. So probability distributions, just like random variables, are either discrete or continuous. And this depends on whether they are for discrete, random variables, or whether they are for discrete random variables or whether they are for continuous random variables. Okay. So in other words, probability distributions are used to describe random variables, like I said before. So if they are used to describe, or when they are used to describe discrete random variables, we call them discrete probability distributions. When they are used to describe continuous random variables, they are called continuous probability distributions. Okay, so like in the assignment I asked you guys to do, I gave you guys some list of random variables, some distributions, and I asked you guys to evaluate some of their properties. Now, you see, there are some of them that are discrete. There are some of them that are continuous. So probability distributions that are used to describe the distribution of random variables, which assumes only countable values, are discrete. Why distributions, okay, of random variables that assume values in an interval are actually continuous. So probability distributions as models, probability distributions, they are actually models for describing the random behavior of data. Okay, they are models for describing the random behavior of data, and then they are appropriately represented by a probability mass function for discrete random variable, or by a probability density function for continuous random variable. So what we do is mathematically talking here now. If we're talking mathematically, um, for discrete random variable, there is a function that we ascribe to it. That function is called the probability mass function. And then for continuous random variable, there is a function we also assign to it. That function is called a probability density function. For probability mass function, we use the short form PMF, and for probability density function, we use the short form PDF. So these are functions that are ascribed to these specific distributions. Okay, so the PMF or the PDF is actually used to calculate the probability that the random variable X is exactly equal to a specific value X, as you can see. Now, we have f of x. This f of x now is actually, it's either the probability mass function or the probability density function. So this probability mass function is used to compute the probability that the random variable x. Now, this random variable x could be discrete, it could be continuous. It is the probability that this random variable x will be assuming a value. You can see this small case x, right? So it's like saying, if I say f of 20, if the random variable is the age of students in our class, if I say f of 20, it means what is the probability that the age of someone in the class, the age of someone in the class is x, which is a random variable, right? What is the probability that the age of someone in the class would be equal to what? 20, or that someone in the class would be 20 years old. So this function here is called the probability mass function. Okay, it's called the probability mass function. So this probability mass function, or it's called the probability mass function if the random variable x is what? Discrete. It's called the probability density function if the random variable x is what? Is continuous. Okay, so the probability it's essentially used to compute the probability that the random variable will assume a specific value. Okay, so that's what a probability mass function or a probability density function is. Okay, so don't forget it. Summarily, the probability mass function is consistent with discrete random variables. Probability density function is consistent with continuous random variable, and it is used to compute the probability that a random variable, whether discrete or continuous, we assume a specific value. Okay, so now outside or beside the probability mass function, we have another function that we use to appropriately describe random variable. This function is called the probability, the cumulative probability function. The short form of it is the CDF. Now, the cumulative probability function. The cumulative probability function. So this is another function we use to describe probability distribution. Okay, because if you are studying, it's very likely you're going to find it in the literature. I mean, you find stuff like PDFs, PMF, then probably CDF. Now, the cumulative distribution function is actually used to determine the probability that a random variable x takes a value less than or equal to a given number. You see, this is different from the one we considered before. Okay, this is different from this. You see, the probability density function is used to calculate specific probability. That is the probability that a random variable will assume a specific value. Okay, the random variable x will assume a specific value. Why the cumulative distribution function is used to compute the probability that the random variable x will take a value less than or equal to a given value. So what we're saying is this. Here, if I say what is the probability that x will take a value less than or equal to 20? Okay, what is the probability that x will take a value less than or equal to 20? Now, if x is discrete, if x is discrete, and that random variable, for example, let's assume the random variable starts taking values from 0. That is the set of possible values the random variable takes begins from 0. Like in the case of age, okay, for anything, okay, if it starts from 0, okay, if the possible values, remember I talked about the possible values that a random variable takes. If the random variable starts taking value from 0, okay, the set of values, okay, and then I want to compute the probability that x is less than or equal to 20. It means I am going to compute the probability that x is 0, probability that x is 1, that up to x is 19, till I get to x is 20. Now, and then I sum them together. This happens when x is a discrete random variable. So what I'm saying here is, if the random variable x, the set of all possible values that x can take, starts from 0, for example. Okay, this is an example. If it takes value from 0, I mean the set of all possible values that x as a random variable can take, if it begins from 0, now, and I want to compute the probability that x is less than or equal to a certain number x. Now, in this case, I'm saying x is 20. This lowercase x is 20. Now, I am indirectly asking you to compute what is called a cumulative probability. Why is it called a cumulative probability? It is called a cumulative probability because I'm asking you to compute the probability that x is 0 plus the probability that x is 1 plus the probability that x is 2 up, until I get to the probability that x is what? 20. I mean, just sum everything together, and that gives me what is called a cumulative probability. Okay, so the cumulative probability is, so if I increase x to say 20, so to say 30, this lowercase x to 30, it means I'm going to compute probability that x is 21, 22, 23, down till 30. And then I add all of these probability together. So what you can find in the discrete case, the cumulative probability is like adding the masses, the probability mass function, until I get to a certain value of x. That is the difference. Okay. Now that is the difference. Okay, but if the random variable x is continuous, I can't add. Okay, or the process is not addition. What do? I just have to integrate the function. I have to integrate this probability density function from the lowest point, that is from 0, for example, till where I'm going to stop, say 20 in this case. So that is for probability, cumulative probability function, the CDF. So now these two models I've described now, the cumulative probability, the probability density function, or the probability mass function, depending on whether it is continuous or discrete respectively, and the cumulative distribution functions are two models that we use to appropriately describe distributions of random variables. Please don't forget them, okay? They are the two models, they are the two mathematical functions or models that we use to describe the probability distribution of random variables. The probability mass function or density function is used to compute specific probabilities, probability that the random variable is going to take a specific value, while the cumulative distribution function or the CDF is used to determine the probability that a random variable will take a value less than or equal to a given number x. Okay. Now, every probability distribution are usually or is usually controlled by a parameter. Okay. Now, in the later course of our discussion, I'm going to take time to explain how parameterization of probability distribution comes in. Okay, so every probability distribution is controlled by a parameter or a parameter vector. Now, these parameter or parameter vector, they determine the shape, the scale, and the location of the probability density function. Okay, now what do I mean by that? Okay, you see, probability distributions are models, and there are various ways we can specify these models. Okay, the differences in the model formulation of various probability distributions are actually determined by the nature of how we parameterize this probability distribution, and of course, their structural forms. Okay, now there's what is called a shape parameter. Many of us are we are aware that we are well of the normal distribution, for example. It has a unique shape, and that shape is like the bell shape, the bell shape. We've seen exponential distribution. The exponential distribution it has this shape where it starts from the top and then it falls asymptotically towards the x-axis. Okay, as the observations increase, as the value of the observation of the random variable increase, the probability falls. That's an exponential distribution. That's an example of a shape of a distribution. So there are parameters that control the shapes of distribution. Of course, the normal distribution do not have a shape parameter because it only have one unique shape. That unique shape is just the bell shape. It doesn't have any shape parameter. But then there is what is called the scale parameter. The scale parameter helps us to determine the scaling of the distribution along the x-axis. For example, in the case of the normal distribution, the scale parameter is sigma. Sigma is the variance, okay? The scale parameter here, that is like the variance or the standard deviation. So that is the scale parameter. Then there's what is called the location parameter. The location parameter tells us where the distribution of the random variable begins. Okay, the location, the point of beginning of that distribution. For example, the location parameter for the normal distribution is the mean. Okay, the mean. So every probability distribution is controlled by a parameter or a vector of parameter. Now, I'd like you guys to understand this. Some probability distribution, in further lecture, I'm going to show you probability distributions and how these parameters comes in. So you may have a lot of questions now, but you can just keep them. You can keep them. Those questions will essentially be answered when we look at probability distribution. So some probability distributions take some have shape parameters, just shape parameters. Some do not have shape parameters. Some only have scale and location parameters. Some do not have location parameters, but they have scale and shape. So it depends on the structure of that probability distribution. And of course, we can always include a location parameter to, I think, any probability distribution. Okay, so that is why in the literature, you often find writings like this, f of x theta. So when you see this is a probability density function or a probability mass function, this is a cumulative probability function. You can see the theta coming in here. This notation is trying to tell you that this distribution, the distribution of this random variable, they are controlled by this theta. Okay, this theta. For example, like in the assignment I gave to us, when you specify the PDF and the CDF of the normal distribution, can someone tell me what the parameters are? Can someone tell me what the parameter is? Okay, the mean and the variance. Exactly.
And the variance. Yeah.
And the variance. Exactly. So it means in that case,
And
it means this
deviation.
Yeah, it means this theta is a vector or parameter. Why is it a vector? Because it contains two parameters now. What are the two parameters? The mean, that is mu, and sigma for the case of the normal distribution. So it has mu and sigma. So that is for the normal distribution. So because we cannot do away with the fact that there are parameters that controls these distributions. Okay, now who can tell me what the parameter is in the case of the Poisson distribution?
It's just lambda, which is the
lambda.
same. Yeah.
So that is it. That is lambda. So it means theta here becomes what? Lambda. That lambda is called the rate parameter. Okay. So it's what about the case of the binomial distribution? What are the parameters? Or what is the parameter of the binomial distribution?
Yeah.
Who can tell us?
We have the mean and the variance, which is
Mean and variance.
No, it's not the mean and variance. No, those are not parameters.
MP, that is the number of events and the
okay, yeah, number of observations.
NP
yes,
and Q.
And Q.
Okay, or you can simply say it's just N and P. The two parameters in the binomial distribution is N, which is the number of observations, and P, the probability of what? Success.
Failures.
That's it. Okay, that is just the parameter that controls the shape of the normal distribution. If you change that probability, or if you change the number of observations, you will see that the density of the normal distribution changes. So any parameter that changes the shape of the density is a shape parameter. Okay, if it changes the shape of the density, is a shape parameter. If it changes the scale of the density, it is a scale parameter. If it changes the location of the density, it is a location parameter. So if you change the number of observations, if you change the probability of success, you see that the shape of the binomial distribution, for example, they just change. So every probability distribution is controlled by a parameter vector, or a parameter if it is just one. So if the number of parameter is 1, we say it is a parameter. If the number of parameter is 2, we say it's a parameter vector. That is, theta becomes a vector that contains these two or more parameters. Now, before we move on, it is also important for us to understand that the set of values in R, you know what R means here? R is just a set of real numbers, because random variables can only take real values, or we assume it takes real values. Of course, it only makes sense if it takes real values. It can't take complex values. So the set of random variables, set of values that the random variable takes in the real number system, that is the real line. R here is the real line. Now, the PMF or the PDF can assume is called the support of the probability distribution. It's called the support of the probability distribution. Okay, now who can tell me the support for the Poisson distribution? I mean, can someone just guess? What is the support of the Poisson distribution? Who can help us with that? Okay, let me just go in with that. The support from the Poisson distribution is from 0 to infinity. It's the same for all discrete distributions like the binomial, the binomial, and of course the hypergeometric. Now, even though it is from 0 to infinity, the support for the binomial, I mean the support for the binomial, the Poisson, the hypergeometric is really not. We can't use this real number. We can appropriately use integers, the set of integers. Okay, that is the support, because it can only take integer value. That is, it starts from 0, 1, 2, 3, 4. That is the set of positive integer. Yes, that's the correct form. Set of positive integer. So the set of possible values that a probability distribution takes is called the support of that probability distribution. So for the case of the Poisson, it takes non-negative integer values, from 0, 1, 2, and so on and so forth. How about the normal distribution? The support of the normal distribution is R, is the entire real line from minus infinity to what? to infinity. That is the support for the normal distribution. In other words, the normal distribution can take negative value, can be minus 20, minus 50, 0, 1, 100, 1,000, and so on and so forth. So the support for the normal distribution is the entire real line. It starts from negative infinity to infinity. So that's the set of values. That is the support for the normal distribution. Now, who can tell me what the support is for the Bernoulli distribution? The Bernoulli distribution. What is the support of the Bernoulli distribution? Can someone help us with the support of the Bernoulli distribution? Okay, now the support of the Bernoulli distribution is just 0 and 1. It starts from 0 and ends at 1. You know, the Bernoulli distribution only assumes two values, 0 and 1. It can't even be 2, it can be 3. It's just 0 and 1. So that is what support means. Now let's see the properties of probability distributions very quickly. Now, let's see the properties of the... Yes, quickly.
Sorry, sir. So we can say the support is like the outcome, the likely outcome. Sample space.
That is the outcomes. That is the outcome. Is it really the outcome now? It's not the outcome. It is the outcome transformed by the random variable, the values that result when we transform the outcomes. Okay. Yes, you could use the outcomes in a very restrictive form, but what we are trying to say is that when you flip a coin, it is actually a Bernoulli experiment, right? Because you're going to get a head or a tail. And if it is a head, you get 1. If it is tail, you get 0. So the possible outcomes for that experiment, for that Bernoulli experiment, is 0 and 1. So it's just 0 and 1. If it is Poisson, it goes from 0, 1, 2, like that. Okay. So now let's see the properties of the PMF or the PDF. Okay, what is the property of the probability mass function and probability density function? So every probability density function is every probability density function is non-negative. The value that your probability mass function or your probability density function is supposed to return is non-negative. It can't be negative. It's always a positive for all values of that random variables within its support. Okay, remember, this is like the support, the general class for the support. Now, another property of the PMF or PDF is that the total area under the probability, David, just write down your question and then we're going to talk about it. Okay, so the total area under the probability mass function or PDF curve is 1. Okay, the total area under the probability mass function of PDF curve is 1. That is, when you sum all the probabilities that the random variable will assume, when you sum the probability, when you sum all probabilities, okay, that the random variable assumes all the values within its support, it's going to give you 1. This applies when the random variable is discrete. That is where we use sum. If the random variable is continuous, we use integral. So when we integrate the probability density function, it's going to give us 1. So this is often called the normalization of probability distribution. When you sum all probabilities, it's going to give you 1. When you sum all the probabilities, in the case of probability mass function, it gives you 1. When you integrate the probability density function, it also gives you 1. So this is called a normalized probability. Now, another property is if x is continuous, the derivative of the CDFs will give you the PDF. Okay? If x is a continuous random variable, when you differentiate the CDF, it will give you the PDF. Please don't forget this. If x is continuous, this is the case where x is continuous. Because if it is not continuous, you cannot differentiate, right? If it is discrete, you find the difference. Okay, I didn't include the discrete case here because we've not really studied how to carry out differencing. Okay, we've not carried out differencing yet. But in our advanced method, I'm going to introduce numerical methods, differencing and so on and so forth. So if you differentiate, a probability, a cumulative distribution function, you're going to get a probability density function if x is continuous. Okay, so don't forget that. Now, for the CDF also has its own properties. What are the properties of the CDF? The CDF lies in the interval 0 and 1. In other words, the value of a cumulative probability cannot be less than 0. It cannot be greater than 1. It lies between 0 and 1. Please don't forget this. Then the CDF is also monotone, not decreasing. In other words, if x1 is less than x2, the CDF of x1 is less than or equal to the CDF of x2. Okay, this is monotone, non-decreasing. In other words, if I'm finding the probability, the cumulative probability of 20, it should be less than or equal to the cumulative probability of 50. That is what we mean by monotone, non-decreasing. So thus, as x increases, as we increase the value of x, the probability accumulates, it gets bigger. So the CDF also always satisfies when this x tends to negative infinity, the limit of the CDF is equals to 0. When x tends to positive infinity, the limit of the CDF is equal to 1. Okay, so that is why you see the CDF lies between 0 and 1. We can say that the CDF, we assume a value of 0 when x here is minus infinity. Why the CDF here, we assume a value of 1 when x is infinity. Now, we have to be very careful. This holds when the lower point of the support is infinity. For example, in the case of a Poisson distribution, okay, you know the lowest number is 0. So the cumulative distribution function of 0 will be 0 because the lowest number is 0. Okay, the lowest number is 0. Okay, then the highest number is infinity. So the cumulative distribution function of infinity will give us what? 1. Okay, so this ensures that x takes value in the entire sample space. Now, the CDF also always satisfies this relation here. So for the discrete case, f of x is the same as summing the probability from, from t, which is less than x, till we get to x, or we are integrating the probability from minus infinity to x in the case of the probability density function. What does this mean? It means that the CDF, it means that the CDF is always, we keep adding the probability till we get to a particular point, or we keep integrating the probability, or we integrate the probability from the lowest point to the point of interest. Okay, I think I've explained this before. Now, of course, the probability in an interval are computed using the formula. Probability of A less than F less than B is the same as probability F of B minus F of A. Of course, this theta is there just to tell us that this distribution depends on theta. Okay, so this is an example of a graph of a discrete distribution. Okay, it's a graph of a discrete distribution. You can see this is the density. This is the probability density function for this discrete distribution. It's an histogram, it's like an histogram. Then we have, this is the CDF of a discrete distribution. You can see that it's a step function. The CDF is a step function and is non-decreasing. It's increasing until it peaks at 1 because it cannot be greater than 1. Okay. Then we also have the PDF of a continuous distribution, which is in this form. So the graph of the PDF of a continuous distribution, you can see the way it is. It is not like this histogram here. It is a smooth function because the PDF is continuous and differentiable. So then we also have the CDF, which also peaks at 1 because it cannot be greater than 1. So this is essentially what probability distribution entails. Okay. So thank you guys for listening. Now I'm going to take questions. Okay. I'm going to take questions.
Thank you very much.
You're welcome. Okay, David, let's have it.